other astronomers that people have heard of, but she was a real trailblazer, and I think it's really enlightening to find out, exactly why a major observatory was named after her. So, who is Vera Rubin? What is the observatory? And then finally, I can get this to work. What will it discover? So those are the first main three topics for today's talk. So let's talk about Vera Rubin. She was born in 1928, so almost 100 years ago, born Vera Florence Cooper, and her family actually has roots tracing back to Eastern Europe, I think Latvia. So you can imagine there's a series of name changes that got her to her family name. But she got really interested in science and especially astronomy very early on. So on road trips, she noticed that the moon seemed to hang in place even as the car was driving. So those are some of her own personal observations that made her interested in learning more about the universe. When she was growing up, she grew up part of the time in Washington, D.C., and so she and her sister shared a bedroom. And because she was the younger of the two of them, she was forced to, they shared the same bed, but her sister got the outside of the bed and she got the inside of the bed, which meant, it was harder for her to get out. But that also meant she slept facing the window, and she often looked out the window and noticed, and the window was pointed towards the north, or at least she could look towards the north. And she realized that the positions of the stars, like the Big Dipper, changed over the course of the night. So again, that was another personal observation that kind of keyed her into learning more about astronomy. When she was a teenager, she bought a big cardboard tube from a linoleum store, and she made a telescope out of it with the help of her father. They acquired a lens from somewhere, and you can tell it's pretty rickety looking, so it wasn't very stable. And she wanted to do astrophotography, and it wasn't a very good mount. And then she later realized that she could just point a camera out the window and do long exposures. So that's an example of one of her long exposure photographs of the stars. And but even as a teenager, she realized that women scientists weren't a thing back then, and she got a lot of resistance from her counselors, from her teachers. But she was still interested in being trained as an astronomer. So she applied and got into Vassar, which was an all-girls school and one of the few schools that offered a program in astronomy. And as a result, she graduated from Vassar in 1948 in 3 years, which is something that you could do back then. And then she also met Robert Rubin, her future husband, in 1947, so the year before she graduated. And normally, it's not, who someone marries isn't really important in stories of scientists, but in this case, this was an extremely important for her, because back then, when women got married, and if they had a career, they were expected to quit their career and become a homemaker and become a mother to the children and raise a family. But her husband was also a scientist. He was getting his degree in physics, and basically he was going to Cornell, where he was getting his PhD. So after they got married, she applied to Cornell to get her master's. And Bob Rubin completely supported his wife in her goal to become a professional astronomer. And so, and it turned out that his support, as well as the rest of their family support, was really instrumental in allowing her to pursue what she wanted to do and to succeed. And so at Cornell, she was mingling with people like Philip, let's say, I'm going to screw up these names, Hans Bethe and Richard Feynman, who was her advisor, and Philip Morrison. But she ended up let's see, get working after Bob got a job in the DC area. She moved with him, and she pursued her graduate degree at Georgetown in the DC area. And she worked with an advisor who was nice enough to her, and he gave her this problem involving the supposed rotation of galaxies. So, for hundreds of years, people knew that the planets orbited the sun. And then by that point, in the middle of the 20th century, we also knew that the sun and other stars orbited a central point in our collection of stars that we know as the Milky Way galaxy. But there was still a question about whether galaxies themselves orbited some common center in the universe. So that's what her advisor tasked her to do. And he had a certain amount of observational data that she analyzed. And we now know that this isn't the case. There isn't some central point that everything orbits around. All the galaxies in the universe are just expanding away from each other. But the results of her analysis actually show that there might be something to this idea. So based on this very limited sample of galaxies, the limits of the data appear to show that this might be the case. And so her advisor thought, well, this is a wonderful result. I think we should present this at the next American Astronomical Society meeting, which is coming up in December of that year. But because you're currently pregnant with your first child and you're due in late October, November, obviously you can't go to this meeting. So I proposed that I go to this meeting in your place and present for you. And back then, it wasn't unheard of, and it was actually quite common for more senior members of scientists to not only present their junior faculty or people under them their work, but they would also take full credit as well. Okay, so this is very common, and I've even read papers where from the 1920s and 30s where you see the author of the paper describe all these results and the conclusions, and then at the very end there might be one sentence that says, well, all this work was based on this one other person's work. So, Vera Rubin, she was pretty strong-willed, and she actually stood her ground and said that she would attend this meeting, and she didn't want him to present in her place. And so she defended her master's thesis in October, and a month later, she gave birth to her son on November 28th, and a month after that, she was presenting at the AAS conference in Haverford, I think it's Haverford, Pennsylvania, which is about, 10 miles from Philadelphia. And so again, this is where her family and her husband came in. So it turned out that her in-laws were in Philly, so they had a place to stay. And her parents drove with her husband and their small child to Philadelphia. So her parents looked after the baby, and then her husband drove her to the meeting, and he couldn't go in, so he waited in the car while she made her presentation. So she made the presentation, and it turned out that there was press in the audience, and she writes about this in an autobiographical essay, and there are also a couple of biographies that have been written about her that mention this, but they don't show you what was published in the newspapers. And so this actually went out through the AP, the Associated Press. And so the fact that she had made this, possibly a momentous discovery of rotation of galaxies around this central point in the universe caused a lot of ruckus in the meeting and amongst the other astronomers. But it also drew attention of the reporter. And so the story appeared throughout the country. And so this was from, I'm trying to remember, the Modesto Bee. So this is in California. And if you look right in the middle of that page, you see the headline, Women Startles Astronomers with Theories. And then there's another headline, which I thought was hilarious. Young Mother has own theory of universe. So back then, they couldn't get beyond the fact that this was a woman and a mother who was able to do astronomical science. But I got this mixed around. So she got her degree from Cornell, but she later went to Georgetown for her PhD, and she eventually got it and continued to do work in galaxies. And then she was hired at the Carnegie Institute in Washington, D.C., and she worked with a longtime collaborator for many decades, Kent Ford, who was not only an astronomer, but also an instrument designer. He built instrumentation, and more specifically, a new type of detector that would amplify, an electronic detector that would amplify the photons coming in from the night sky so that you could get you could measure the electrical signal as opposed to trying to detect via just photographic plates. And so she worked on lots of different scientific projects, astronomical observations of mostly galaxies, but also of stars. But what she's most well known for is studying something known as the rotation curve of galaxies. And so effectively what you do is you measure the velocities of stars in a spiral galaxy. So our Milky Way galaxy is a spiral, and you can think of it as a big disk, like a big pizza, and all the stars in that disk orbit around the center. And if you just think about the visible mass that we see in the galaxy from the stars, and you think, well, that the stars should trace the amount of mass, if you assume a one-to-one relationship, what you find is that what you would expect is that if you measure the velocities, the Doppler shifts, the motions, the velocities of the stars should actually decrease with distance. So it would be highest towards the center, and then as you go further and further out from the center, there should be a shallow slope, so it should drop. And this is sort of similar to what we see in our solar system. So most of the mass in our solar system is in the sun, and if you made a plot of the velocities of the planets in their orbits, you actually also see a drop in velocity. So Mercury goes around the fastest, and as you get further and further out, the orbital speeds go lower and lower. And this has to do with most of the mass being concentrated in our solar system in the sun. So the strength of gravity drops as you get further out. And galaxies are the same way. So spiral galaxies are brightest at the centers, and then the disks gradually get dimmer and dimmer. So you can sort of assume that most of the mass is in the center, and there's less and less mass as you get further and further out. And so similarly, you should see a drop in the velocities. But here is their plot for the Andromeda galaxy, or M31. This is the closest large galaxy to us, just over 2 million light years away. But instead of dropping, you can see that the points are sort of flat, or you can draw a roughly flat line through them. And this wasn't the only set of observations. Other astronomers followed up, and they continue to do work for many other galaxies. So this is exactly the same plot as before. You can see those exact same points, but these other points are from radio astronomy. So these are from radio astronomers looking at gas clouds in the Andromeda galaxy, and they exactly have that same trend. Whereas instead of having the velocities drop, the velocities stay more or less constant. And like I said, Rubin and Ford continue to observe lots of galaxies. So these are rotation curves of more than a dozen, about 20 different galaxies. And you can see that same trend, that same phenomenon. And today, what we know is that this is the first direct observational evidence for dark matter. And so what this suggests is that instead of the matter in the galaxies just being traced by the visible light, by the stars, there's some invisible matter whose only evidence that we have is its gravitational tug, or its gravitational pull on the visible matter. And so if you infuse these galaxies with this halo of invisible dark matter, you will basically get the rotation curves to match what is observed observationally. So even though people had suggested, even back in the 1930s, when Fritz Zwicky observed galaxy motions, there was some hint that dark matter existed way back then, but that wasn't published in a journal that was widely read. And so this was really the first time that this evidence for dark matter kind of was visible enough to really slap astronomers in the face and forced everyone to reckon with it. And so she continued her work, and she was recognized for her achievements. So she was elected to the National Academy of Sciences in 1981. And so this is something that that is done by your peers, by other very well-renowned astronomers. She was given the U.S. National Medal of Science by Bill Clinton in 1993. And this is the highest honor a scientist can have in the United States. And then finally, whoops, jumped ahead. She was honored with the Vera Rubin Observatory named after her, and this was actually done by an act of Congress. So this was signed into law in January 2020. So given her history and growing up and living through this time where women weren't expected to be scientists, Vera Rubin recognized the fact that she was very lucky in having that support. I mean, of course, she was also very strong-willed, and that helped as well. But she ended up being a real champion for women in science, especially for younger researchers coming up, whether they're graduate students, or postdocs, or young faculty. And she would write letters of support to students out on their job hunts. And one time she got back a letter from, let's see, I think this is for a faculty job. And this is from the committee at the university that her former student was applying for. And the other faculty member wondered if, I mean, they really wanted this particular student who was a young woman. And they asked Vera Rubin if she could advocate for that particular university, that particular department. And so Vera Rubin replied, well, I went and looked at your program. It doesn't look like you have any other women faculty, and I'm not sure what support you might give to this young researcher. So until I see suggestions that that's not the case, I'm going to suggest to her that she not accept your job offer. So she was pretty blunt about things like that. And I just, and one other thing is that women were actually denied use of telescopes. They weren't allowed to go observing, and the excuse was there's only one bathroom, so obviously you can't have a woman up at the observatory where you could accidentally run into a man in the bathroom. So they were denied use of telescopes until the 1960s, and then she was part of this push to really open up observatories to everyone, not just men. And just want to close with a couple quotes from her. Worldwide, half of all brains are in women, and don't let anyone keep you down for silly reasons. So these were, aphorisms that she really lived. So given all that, let's jump to the Vera Rubin Observatory. And this is a major undertaking funded by the U.S. National Science Foundation, as well as the Department of Energy. And what the Vera Rubin Observatory is not only the major, enormous telescope, an 8-meter class telescope, but the mission of the observatory is also very different. So instead of just targeting observations at select portions of the sky, what it does is it maps the entire sky over the course of 2 to 3 nights, and it does this repeatedly for 10 years. So the goal of this observatory is to basically create the highest resolution time-lapse movie that we have of the entire sky. So you're looking for changes in the sky. You're also mapping the sky to extremely deep magnitudes, meaning you're able to see extremely faint things and seeing how distant galaxies might change with additions of appearances of supernova, but also mapping the web of galaxies. And the origin of this observatory actually goes back to the mid and late 1990s. So this gives you an idea of how long it can take these monster observatories to gestate before they come into existence. And a lot of that can be traced to Tony Tyson, who's an astronomer at Bell Labs. He, at the time, was actually interested in mapping galaxies to try and study dark matter and to trace dark matter. And he was building instruments at Bell Labs. And so this was one of the instruments that he had made, which consists of 4 detectors, 4 CCDs. And I'm not sure how many pixels there are. There might be only 512 by 512, maybe 1024 by 1024. So this is a camera that is tiny in the amount of resolution, the amount of imagery that it can capture on the sky, compared to even what you find on your phones in your pockets and purses. And so he had hauled us to an observatory in Chile, in South America, and they were using this to map little tiny postage stamp size patches of the sky. And he was wondering, well, this is taking so long to get the science data that I need. What can one envision to create something that would map far larger swaths of the sky and allowed him to do this work more efficiently and much faster? And so that's when he started drawing diagrams on backs of napkins and envelopes. And he ended up working with Roger Angel at the University of Arizona. And Roger Angel is best known in astronomy for basically creating the Mirror Lab. So if you go to the University of Arizona and go underneath the football stadium, he's actually constructed this huge laboratory where they melt glass and they spin it and use that spin to basically shape do a first pass shaping of the telescope mirror. Because that the spinning liquid gives you a paraboloid, and that's what you want for the shape of the mirror. So they worked on this, and I'm going to skip all the details, but basically, after so many decades, they ended up constructing the Vera Rubin Observatory. I have to be very careful again. Down in Chile, at a place called Cerro Pachon, which is not too far off from Cerro Tololo, which is where an existing observatory is. So this is north of Santiago. And Chile is a place where many large observatories are, just because you're in the high desert, mountainous region of Chile. It's dry, it's relatively, you get lots of dark skies because you're far away from cities, and you also get dry air and pretty clear conditions for most of the year. And so this is at over, I think, 8,600 feet in altitude. And because you're at the top of a mountain, the other thing is you get nice airflow. Just run this video showing the construction, which took over 10 years. So they had to clear off this particular mountaintop. And if you think about airflow, air flowing over a mountain peak or over a ridge becomes turbulent as it moves past that ridge or past that peak. So you want something at the top of a mountain before it gets turbulent. And so that's why observatories are placed at the top of the mountain, not only because they don't want anything blocking their view, but also to have that laminar airflow, because as soon as the air becomes turbulent, that affects your seeing. Instead of a steady pinpoint of light for stars, you get jittery motions. And so we're seeing the observatory take shape, and this is actually an enormous structure. It's about 18 stories high from the bottom all the way to the top. And so you have the dome that houses the telescope, but there's also a service building that's attached to it. So that's why you can see that structure that kind of goes off to the side and down. And And it is also decided to go with this kind of blue-green metal support structure. So you'll see that their website and these slides continue that color theme, which is, I think, kind of an interesting aesthetic choice. So the reason why you have a giant dome or enclosure for the telescope and the mirror, obviously, is to help protect it during the day, protect it from dust, dust storms, and other things that you don't want a bird coming in and smacking into the mirror, for instance. But if you have a big enclosure, that also means the enclosure heats up during the day, and then it starts to cool off at night. And as soon as you have a temperature difference between the air inside and the air outside, you can imagine that also creates turbulence as well. So you might, if you look closely, you'll see there are these giant vents that are cut into the side of the enclosure. And so those are open at dusk. And so and they might even have fans actively blow air through just so you have consistent air temperature. And this is something that astronomers realized really in the late 80s, early 90s. So they actually went back and started cutting vents into existing telescope domes. But now all telescopes, with enclosures have these vents to make sure that you can equilibrate the air temperature quickly between the inside and the outside. So you can see this enormous thing finishing up. Its construction by sometime in 2022. And that gives you a sense of scale. If you look at the little tiny people at the bottom, as well as the vehicles, of just how enormous this telescope is.
Do they have 2 bathrooms?
Yes, I think they have more than 2 bathrooms. Quite a many more. All right, so let's keep going. So again, like I said, the idea behind this is to map the universe and create not just a map, but a time-lapse movie. And in order to do that, there are 3 novel, important technologies. One is the mirror design, which is very compact, as we'll see. The second part is the ability to see a really wide patch of sky all at once, so that you can quickly map the sky. And then finally, this ability, this program to have detectors that can map to sufficiently faint magnitudes, and also to do it in multiple colors so that you can get the information that you want from your objects. So the first part is the novel mirror design, and it actually uses 3 mirrors and also multiple lenses. So the mirror at the bottom is the main primary mirror. It's 8.5 meters across, and light from the sky bounces off that to a secondary, which is about 3.5 meters, so over 10 feet across. And then it then gets reflected to a tertiary, the third mirror, that's actually embedded in the primary. And then there's some lenses that do additional focusing. And what this allows you to do, because you folded the optics in on itself. So if you think about the telescopes, or traditional idea of a telescope, Vera Rubin's first telescope that we saw a picture of, or if you go to Target and buy one of these telescopes that have a long tube, even regardless of whether they have a mirror or a lens, if you have a large tube-like telescope, and the Hubble Space Telescope sort of falls into this category. If you think about the Hubble, it's kind of like a long tube. But if you're trying to map the sky really quickly, and you're moving from one position to the next, you have a long tube. You can imagine that jumping from one position to the next, there might be some small amount of vibration and you have to wait for the telescope to settle down before you can take your next shot, right? So by having a very compact telescope, that means you can actually pivot and move the telescope around much more quickly than you would if you had a much larger structure. So you're reducing the amounts of potential bend and vibrations. Do you have another question?
Do they make these mirrors in Arizona also?
Yeah.
So they're still making
them? Yep, they are. So here is a little video just showing exactly what I talked about the mirror that was designed, and we'll even see the napkin or the back of the envelope that Roger Angel made. And back then it was called the Dark Matter Telescope because the goal was really focused on dark matter. But as we'll see, the Vera Rubin Observatory is powerful enough not just to look at dark matter, but lots of other things as well. And so we saw that it's pointed out that it has a 3-degree field of view, and the full moon is only half a degree across. So basically the field of view means that you can capture a patch of sky of 6 full moons across. So that's pretty big. And then here is how it plans to scan the sky. So it does each of those shots, one single image, once every 30 seconds. So that's amazingly fast, being able to do that. And so it maps the visible part of the night sky, visible during that time of year from the southern hemisphere, once every 2 to 3 nights. And so over the course of a year, it'll capture the entire sky, and then you'll be able to, obviously you have to come up with ways to detect all the changes in the sky. And we're seeing some pictures of the process that made the mirror, where they put in the blocks of glass before it's melted. So let's look at casting and polishing the mirror. So here are the blocks of glass. We use something called borosilicate glass, which doesn't expand very much when you have temperature changes. And then they have a giant mold where they put the blocks of glass, and then that whole thing is basically a giant oven as well. So it melts the glass and then it spins it. So you can see the blocks melt. And here's that giant oven from the outside. And they're removing the lid of the oven after it's finished spinning and cooling off. And that's how big the mirror is for an 8.5 meter mirror. And now you get the rough figure from the mirror, but you still have to do the fine polishing to get it to exactly the right figure that you need it. And of course, there's the tertiary mirror that's embedded in it, so it's not a standard mirror. And then they have to pack it up and ship it off to Chile. So here's that picture again, just to give you an idea of just how big that mirror is, sitting underneath the football stadium. You have to remember where this is. Question?
So it said 5 tons of glass were removed. How much does the whole thing weigh?
I'd have to look it up. I don't actually know. I mean, it's definitely tons and tons. Not just the mirror, but the whole enclosure that the mirror is part of, as well as the, we'll see in just a minute or two, but everything that's required to move the mirror, there's an 80-ton, or there's an elevator that can move 80 tons of weight. So, all that is less than 80 tons, that much I know. But I don't actually know how much the glass weighs. All right. So you have the glass in the mirror, but you still have to coat it to make sure that it's optimally reflective. And so, through simulations, they realized that they could do coatings of aluminum and silver. And this is actually at the observatory. So that service building has this facility that allows them to coat the mirror on site. And so this was a giant machine built in Germany by a company in Dresden, and so they have these sprayers that actually spray molecules of silver or aluminum. So you can see how it goes from just a mirror blank to this amazing layer where they have multiple layers of adhesive before they spray on the final, whether it's silver or aluminum, and then they spray on a protective coat as well. So even though they have the enclosure, they expect that dust blowing in will mar the glass over time. Here it is. I mean, that's just beautiful. It's amazing that they're able to do that with just this enormous piece of glass. So they expect that every 5 years or so, they'll need to recode it. Actually, I'm going to misremember which. So the secondary mirror requires recoding, and the primary and tertiary requires it as well. And I think one of them is 2 years. And yeah, the primary is every 2 years, and the secondary is every 5 years. So they have to take this down and recode it. So the question is, how do they actually take it down? And I mentioned this elevator, so we're going to see this elevator in action. So there's the entire thing that weighs less than 80 tons, because that's how much the elevator is rated to. And as you can see, the elevator is actually part of the building. You actually see the elevator from the outside. So look at that. I mean, looking at this, it looks like this is a Bond villain's lair, or something you might see, that S.H.I.E.L.D. might create in the Marvel Cinematic Universe. It's just absolutely nuts that they created this, and then it goes to be installed in the telescope. And I'm only showing just a handful of videos, but if you go to the Vera Rubin Observatory website, and if you poke around, you see other videos showing other aspects of the installation and videos about their instruments. So let's just keep on going. I thought this was really interesting as well, because how do you clean a mirror? Well, you do it with liquid CO2. So I know about CO2 in gas form and CO2 in solid form, but I'd never heard of liquid CO2. So there's no way to make CO2 liquid enough to create a spray that comes out of a hose that you can use to clean the mirror. So this is fun to see. All right, so let's talk about the detector. The detector is basically something that's about the size of a medium-sized car. And it's not just one detector. There are 189 CCDs, or individual detectors. And each of them is 4K by 4K, meaning 4,000 pixels, 4096 by 4096. So that's on, what is that, 16 million pixels, and times 189. And it gives you total about 3.5 degrees. And this circle right here is the full moon for scale. So that gives you an idea of just how big a patch of sky the telescope captures with a single pointing. And then it has to do many hundreds, thousands more pointings in order to capture the entire sky during the course of a night. And then there's also a bunch of filters that are used to capture just only a particular color of light, so that it can do the science that it's designed to do. So here is all of the different parts of the camera, from the lens assembly and the filters to the different lenses and the detector in the middle of all that. And these are some of the largest lenses that have ever been devised. Actually, they might be the largest. They're on the order of 3+ feet across. And they use a standard set of filters that are used quite a bit in galactic astronomy, but they range from the ultraviolet all the way into the far red and into the near infrared. So by just looking at these different filters, and actually by comparing observations in different filters, you can actually get a lot of information about stars and galaxies. And then the filter array itself is also really interesting, because you need to be able to swap those 6 filters in and out relatively quickly. And so they have this mechanism that rotates a filter into place as needed. And so this is done slowly to show you how that works. So all pretty innovative design and huge amounts of really interesting engineering that went into pretty much every single aspect of the observatory and the telescope. So we're looking at 6 different colors, and there are lots of different types of observations or observational programs that the Vera Rubin Observatory can make, but the main goal, the original science objective was to study dark matter, and now we also know about dark energy, this mysterious force in the universe that causes the universe to expand faster and faster. And so the idea to understand dark matter and dark energy is to map as many galaxies as possible and as far away as possible, because light travels at a constant rate, 189,000 miles per second. But what that means is the further you look, you're also looking further back in time. So not only are we mapping galaxies, but we're mapping galaxies as they evolve through time in the universe. And by mapping this web of galaxies, we can see how they evolved over time. And then that, along with theorists and computational astrophysics, you can get a better understanding of what the dark matter network looks like, and also get information about how dark energy is causing the universe to expand faster. And so back in June, they released some of their first images as well as videos of exploring these images. So this is the Virgo cluster of galaxies, which is about 50 million light years away. So, it's pretty close by, cosmologically speaking. And through our optical telescopes, we know there are about 2,000 galaxies that are all loosely gravitationally bound in the supercluster. But because Vera Rubin is not looking just at this cluster, but all the galaxies that are behind it, it's found on the order of about 10 million galaxies just in these. And this is actually two different pointings that are added together. So basically, every single smudge that you see in the background, everything that looks like just a little point of light, that's actually an individual galaxy that's much, much further away than what's in the Virgo supercluster. Now, as it's mapping the distant universe, it's also looking at everything that's in front of those galaxies. So not only are there, Vera Rubin will also be mapping the stars in our own Milky Way, but there are also objects in our own solar system as well. So you can imagine there's a lot of foreground objects. And so we think that it will be discovering many, many new asteroids and comets as well. So in the same set of images that were used to look at the Virgo cluster, they were also finding lots of asteroids. So asteroids are easy to spot because if you look at them from multiple images, they're the objects that are orbiting in our solar system. They drift or move relative to the background stars and galaxies. So here are all the asteroid discoveries. The first night alone, so these observations were done over about 10 nights, only about 10 hours of total observations. But the first night they found over 900 new asteroids. And over the course of those 10 nights, they found over 2,100 new asteroids. And again, this is on the order of about 10 hours of total observation, because they're still commissioning the telescope. So you can see the new asteroids found within, so that's the light blue, and then that sort of dark blue donut are the existing or known asteroids. So we think that Vera Rubin will be finding millions of new asteroids. And if you think about it, currently with all the other telescopes on Earth, astronomers find about 20,000 new asteroids every year. And Vera Rubin found 1/10 of that in a little over a week. All right, so how can you see this? It turns out that you can actually go and explore these data sets yourself. Skyviewer.app is actually a web address, so you can look at it on your phone, on your laptop, on your tablet, and it's an app that allows you to zoom in to the highest resolution possible. So if you go to the website, this is what it looks like, and then you just one link, and here I'm showing what it looks like on my browser on my computer. So this is the Virgo cluster, and here I'm zooming all the way in, and you can see the resolution improve. So again, all those individual smudges that don't look like anything, those are actual galaxies. And over time, as the observatory gathers more and more data, they'll be posting the kind of cleaned up versions for the public to look at. So the first major data release will be next summer. So sometime, another 6 to 8 months from now, they'll be releasing an all sky. So not just one portion of the sky, but the entire sky is visible from the observatory that you can explore. Yes?
With the very high resolution images and that far away, how do they get the data up to the servers that hold all that?
That would also require a huge amount of infrastructure. So I think I'm trying to remember what the numbers are. Let's see. I think I have it here. I have some. Oh, here we go. Let's see. Yeah, so they're expected to get down about 20 terabytes of data per night, and over the course of the entire 10-year mission, they expect to have about 500 petabytes of data. So petabyte is 1,000 terabytes, and so that's an enormous amount of data, and they had to basically lay down 2 dedicated fiber networks, one going from Chile to Florida, and then another one going from Chile to Europe as a backup. So you have 2 data streams, and I think the other fiber ends in France. And so we have storage for all that data, and then they'll also do a huge amount of processing before any astronomer looks at the data. And because there's so much information, they also have to write lots of algorithms to do basically compare and contrast. So you have an image of this part of the sky, you compare it to the last image that was taken at that same exact part of the sky, and you can blink between the two of them. You can look at them to see what, if anything, has changed, but you can also write a computer algorithm that also detects changes. So it'll be able to, so that's how it was able to find those asteroids. It'll be able to find novas, supernovas, really anything that changes in the sky. And astronomers that have particular programs, research programs, if there are astronomers who want to observe new supernovas, they'll probably get alerts. There are probably going to be hundreds, if not thousands, of new supernova discovered each night, and or over the course of a couple nights. And so they'll get alerts about all of them, and then they can decide which ones they want to follow up on. And other astronomers who have other interests, maybe they're looking at how black holes and centers of supermassive black holes cause the centers of galaxies to fluctuate in light, or other phenomena that are time-based. They'll be able to follow up once they get their alerts. And one other aspect of this, let me just cycle through this. Is that there will be a citizen or community science component as well, because there are lots of astronomical research programs where it's, even today, before the advent of Vera Rubin, there's so much data that's coming down that it's impossible for any one human to look at or to examine. And so for many years now, there have been citizen science projects where you can actually sign on and do things like galaxy identification. And so the Vera Rubin Observatory does plan, although nothing has been officially announced, I do know that they have plans to come up with science projects that you yourself can sign on to, where you get a little bit of training, and then you, along with thousands of other volunteers, help astronomers identify objects that they might want to follow up on. And so I just want to end with this quote from Vera Rubin, who, which I think sort of encapsulates both her life and her work, as well as the observatory that's named after her. Don't shoot for the stars. We already know what's there. Shoot for the space in between, because that's where the real mystery lies. And I think if you look at the history of new instruments, new telescopes, new spacecraft sent out to distant planets, when we have something new, some new technological breakthrough that allows us to see the universe in a way that we haven't seen before, almost every single time, the discoveries that those novel, innovative technologies, instruments, spacecraft make, we cannot predict what we'll learn from them. So I think it's a really exciting time to be interested in astronomy because there's going to be a lot coming down the pipe. So thanks everyone, and I'm happy to answer any questions that you might have. Yes, back there.
Wait a second. Now that the telescope is being used, what's the growth in the number of observed galaxies in the universe from pre-telescope to now?
Yeah, so I think the number that they're expecting for the total new number of galaxies that Vera Rubin will find will be on the order of, I think, 10 billion. And the only reason I remember that number is that the other factoid that came with that number is that for the first time, we will have knowledge of more galaxies than there are humans on Earth. So before then, all the other surveys, they usually involve discovering millions or tens of millions of galaxies. But this is the first time where the number of galaxies will exceed the human population on Earth.
So what do astronomers think? Life elsewhere in the universe?
Well, life elsewhere in the universe, that's a totally different question that Vera Rubin won't be able to answer. But because there are other, if you think about it, Vera Rubin is designed to look at a big patch of sky. And if you think of life as, whether it's non-intelligent life or even intelligent life, they're usually coming from a planet, that's around one star. So you're looking at a target that's much, much smaller than what Vera Rubin is capturing. So, so that's a different discussion, although I'm sure there's far smarter astronomers than me who can probably come up with an explanation of how Vera Rubin can help you find life elsewhere in the universe. Yes?
I'm trying to understand kind of how to differentiate between how cameras work and how the telescope works. And I'm curious, when we use our cameras, we can focus, we can zoom in, we can focus so that the focus happens at a distance. I'm wondering if the telescope has the functionality so that it's not just taking flat pictures at the same zoom or focus level, that it's, in this case, that on one night when it's taking a certain slice of the sky, perhaps it's focused at a distance that would equate to 100 million light years, and at one point it's 2 billion light years. Is that happening so that it's taking, so to speak, zooms or focal points at different distances as it's taking the sky?
Yeah, that's a really good question. Well, it turns out that in astronomy, you don't really have to worry about focus because effectively anything out there is effectively at a focus of infinity. So you just, so unlike, so the Vera Rubin Observatory or any professional observatory run by astronomers, you can't use them to peek at your neighbors because their focus is set to infinity. So, I mean, you can, but it'll be a fuzzy image. So, effectively, whether it's in the solar system or outside the solar system, the focus will be the same. But great question.
Before you have one more question?
Yeah, these days one of the problems with observatories are these satellites, Starlink satellites in particular. And I can imagine if you're looking at a huge part of the sky, you're going to have hundreds of these orbits of these satellites. So how does this telescope deal with that?
Yeah, that's a really good question about Starlink satellites, the fact that we're launching these constellations of satellites for internet service, for communications that are blanketing low Earth orbit. And so how do observatories deal with the fact that they're getting photobombed? And this is something that astronomers started worrying about because the first Starlinks were launched in 2019, 2020. And they started, and so the astronomers noticed before anyone else that this was happening because they started seeing these streaks running across their images, and and these are problematic because the satellites, well, they have a solar panel that's pointed towards the sun, but they also have a radio dish that's pointed at the Earth, and then depending on where it is in its orbit and where you are on the ground, you will see, basically a bright object, and that brightness might vary over time. So it typically gets brightest when it's high up, and then the brightness diminishes as it gets closer and closer to the horizon. But currently we have about 12,000 satellites in orbit, and that's up from about 6,000 or 7,000 just 7 or 8 years ago. And it's not just SpaceX and Starlink. So Amazon is planning their own constellation. It's been recently renamed to Amazon Leo from Kuiper. There's a British company that's planning one called OneWeb. The Chinese have been launching them, and there are other nations, because they realize that these satellites are really important for their national security, for war, as has been shown in Ukraine. It's kind of unstoppable in the sense that we will get more and more of these satellites, and that's a concern for a lot of reasons, but for astronomers, that does have an almost existential risk. So I know that the Vera Rubin people have done simulations where, based on projections of how many satellites will be going up, they say that this might affect some fraction of their observations. I think it might be on the order of 10% or less. So that means that they'll get only 90% of their observations because they have to throw away ones that are harmed by the satellite trails. And there are ways in which you can try and remove the effects of the trails, but if the satellite is so bright, it actually causes the detector to, what the detector does is it amplifies the signal so that one photon hitting might result in X number of electrons. But the number of electrons that can be so much that it totally fills up the well of that particular pixel, in which case you've actually lost all information because you've saturated that pixel. But it can also happen so that you have so much overflow that it starts overflowing into adjacent pixels. And if it's so bright, you start saturating those pixels as well. So up to a certain point, if they're not saturated, you can actually remove that extraneous signal. But if it's saturated, there's really nothing that you can do. So it all depends on how bright these are and how many they are. And if you lose 10% of your images, but if you increase your budget so that you increase the time that you're observing by an extra 10%, you can make up for it. But if you don't get that budget increase, you don't fully make up for it. And there are people trying to mitigate the effects of satellites, of these bright satellites. So astronomers have been talking with SpaceX for many years now. And so they actually tested painting some of their Starlink satellites black just to see if that could reduce the reflection. But that had additional problems because it increased the heating. So because now you painted it black, it's going to warm up more. So some of these things have to be redesigned, but there are no regulations concerning what you can put up into space. So it's not just SpaceX that you have to talk to, it's all these other companies and also other nations as well. So it's definitely a problem, and there are possible solutions, but it's uncertain how much the impact will be.
Before we let you go, can you give us a rundown of what you've been working on at the Denver Museum, the 4 projects that you told us?
Yeah. So Rick and I were talking about this, and so I do a lot of work with our digital planetarium, as hinted at in my bio that Rick read. And one of the things that I do is, instead of using the planetarium to look out into space, we turn our gaze back towards planet Earth. So I've been running a series of programs called Digital Earth, and they only happen a few times a year. So you have to, once you see it, you have to sign on really quick to make sure you get a ticket. But we use the planetarium to fly over the Earth like an astronaut would, but to explore, plate tectonics, water, groundwater, Colorado River. We did a program on energy last August, and I just came back from North Carolina to learn about the impacts from Hurricane Helene. So last year, so we'll be doing a program on hurricanes. And what's really fun about the planetarium is that I go out and take 360-degree panoramic photography. And so when we fly down to a location on Earth, we actually land, and you'll actually be immersed in that location. And I work with a geologist, so it's not me talking. I don't consider myself an expert on the Earth, but we concoct these really fun presentations using visualizations in a way that you don't really encounter anywhere else. And so not only do you learn a lot, but they're done in a really engaging way. So I think we're planning to have one in January, which will be our 100th show, and it would just be about kind of I think we settled on something like Our Changing Earth and humans on Our Changing Earth. I haven't quite figured out what the title will be, but we'll have a program on hurricanes, a program on energy, and then one on Venice. I think we're going to try and do that as well, because we have a traveling exhibit coming out next year that we think will involve Venice, and I think we can latch onto that. So that's not entirely certain yet, but we hope to do that as well.
Is there like a newsletter you can sign up for?
Yeah, if you're a museum member, and even if you're not, you can probably sign up to see what events are coming out through the museum. And so they usually make an announcement about 3 to 4 weeks before the event about things that are coming out.
Is there one showing?
Yeah, unfortunately, it's kind of a one-off. We try to, when there's popular demand, we try to do 2 shows that night. But because it's a kind of a special presentation and it involves live speakers, we don't do more than 1. So, but we've been taking them on the road. So, December 9th, we will be repeating our energy program up in Fort Collins at the Fort Collins Museum of Discovery. So if you're interested, if you want to drive up to Fort Collins that night, I think it's going to be either at 6 or 7. So you can spend the day at Fort Collins and see a planetarium talk and come back a little late, because it's kind of a far drive from here.
All right, let's give Dr. Yu another round of applause. So we plan on coming back in a month, and we'll hear something about vibe and coding with AI. Okay, thanks everybody for coming. Have a great day.
Thanks, everyone. Okay. Well, thank you. That's just fine.
Oh, that's fantastic. We have so much to learn from you. We learned so much already.
One thing I want to say is
Yeah.
during COVID,
Yeah.
we're members of the museum, and
Yeah.
we would watch the programs. Was it every Wednesday or something, or every Thursday, whatever? We would watch those. That helped us get through COVID. So thank you.
Okay, okay. Did you see the Digital Earth programs?
Yeah.
Okay, okay. Yeah, those are exactly it. Yeah.
Yeah. Those are awesome.
Yeah. Yeah.
Thank you.
Yeah. So, yeah, if you have a chance, come see us live in person.
Yeah.
Yeah. Yeah.
Very good. I really enjoyed